There's a conversation happening right now about when solar energy will dominate the global energy system. Optimists say 10 years, pessimists say never. But both groups are missing something crucial, something that history has already shown us twice before. Energy transitions follow patterns, predictable patterns that span decades and reshape entire civilizations in the process. And if you understand these patterns, if you can read the signals that coal, oil and natural gas left behind as they rose to dominance, you can see exactly where solar stands today and where it's headed tomorrow. The question isn't whether solar will become our primary energy source. The question is how long that journey takes and what obstacles lie along the path, because every energy source that came before solar faced the same challenges, the same resistance, the same infrastructure gaps, and every single one took far longer than anyone expected to actually reshape the world. This is the story of energy transitions, 3 complete cycles that teach us everything we need to know about the 4th one happening right now. Let me take you back to 1800, when the world ran on wood. Forests covered the landscape. Cities burned firewood for heat and cooking. Factories relied on water wheels turning beside rivers. Transportation meant horses pulling carts along muddy roads. The energy system was simple, local, and incredibly limited. If you wanted power, you needed trees nearby or a river flowing past your door. This worked fine when populations were small and economies moved slowly. But by the early 1800s, something was changing. England was running out of trees. Centuries of cutting wood for shipbuilding, construction, and fuel had stripped the forests bare. Firewood prices were climbing. Charcoal, which required enormous amounts of wood to produce, was becoming expensive enough to threaten the iron industry. Cities were growing larger, consuming more energy than the surrounding countryside could provide. The old system was hitting its limits, and people knew it. They needed an alternative, something more concentrated, more abundant, something that didn't require replanting forests and waiting decades for them to grow back. Coal had been around for centuries. The Romans used it. Chinese miners dug it from shallow pits. But coal was dirty, smoky, and harder to work with than wood. It required mining deep underground, transporting heavy loads, and dealing with toxic fumes. Most people preferred the familiar warmth of a wood fire to the sulphurous smoke of burning coal. The transition didn't happen because coal was better in every way. It happened because wood became too expensive and coal became necessary. Here's where the timeline becomes important. Coal didn't replace wood overnight. In 1800, coal represented just 1.7% of the global energy mix. Wood still dominated, water wheels still powered most factories, horses still moved goods and people, but coal was growing, slowly at first, then faster as infrastructure developed. By 1850, anthracite coal was flowing through new canal systems in Pennsylvania, reaching cities along the eastern seaboard. By 1870, railways built with coal-powered steam engines were spreading coal even further, creating markets in places that had never seen the fuel before. The critical moment came around 1880. This was when coal finally overtook wood and biomass as the primary global energy source. Think about that timeline. 80 years from 1.7% to becoming the dominant fuel. Not a decade, not even 2 decades. 80 years of steady, grinding progress. Building mines, digging deeper shafts, constructing railways to move coal from mines to cities, training workers to operate steam engines, convincing homeowners to switch from wood stoves to coal furnaces. Every step took time, capital, and effort. By 1900, coal had captured 47.2% of the global energy mix. It powered factories across Europe and America. It fueled the locomotives that connected continents. It generated electricity in the new power plants springing up in major cities. The Industrial Revolution ran on coal, and coal had reshaped civilization in the process. But it took a full century to get there, from 1800 to 1900, 100 years of continuous expansion. Now here's what makes this pattern instructive. Coal didn't just replace wood, it created entirely new industries that wood could never support. Steelmaking required the intense heat that only coal could provide. Railways needed the power density of steam engines burning coal. Electricity generation at scale demanded fuel that could be stockpiled near power plants and burned continuously. Coal enabled things that were impossible in the wood-burning era, and those new capabilities justified the massive infrastructure investment required to make coal ubiquitous. But even as coal was reaching its peak, another fuel was emerging, one that would eventually challenge coal's dominance. Oil had been known for centuries. Ancient civilizations collected it from natural seeps and used it for waterproofing and lighting. But large-scale commercial production didn't begin until 1859, when Edwin Drake drilled the first successful oil well in Pennsylvania. That well produced crude oil that could be refined into kerosene, a cleaner-burning fuel for lamps than the whale oil and coal oil people had been using. Here's what's fascinating about oil's early days. It wasn't immediately obvious that oil would become the dominant fuel of the 20th century. In 1859, oil was mostly a replacement for whale oil in lamps. It had no role in transportation. It didn't power factories. Steam engines burned coal, not oil. The infrastructure for oil, the refineries, the pipelines, the distribution networks, none of that existed yet. Oil was a niche product serving a specific market, lighting, and even in that market it competed with coal gas and other alternatives. The timeline stretched out over decades. Oil was first commercially produced in 1860, but it took 50 years to reach just 10% of the total energy market. 50 years to capture 1/10 of the market. Then it took another 30 years, from 1910 to 1940, to increase that share from 10% to 25%. Do the math on that. 80 years from commercial production to reaching a quarter of the energy mix. And this was with a product that had clear advantages over coal. In certain applications, it was liquid, easy to transport through pipes, and had higher energy density. What changed oil's trajectory was the automobile. Henry Ford's Model T, introduced in 1908, began the mass production era that made cars affordable for ordinary people. But even that didn't immediately transform oil into the dominant fuel. In 1920, most American families still didn't own cars. Cities relied on streetcars powered by electricity from coal plants. Factories ran on steam engines, burning coal. Oil was growing, but coal still powered most of the industrial economy. The real shift came after World War II. Between 1945 and 1970, oil consumption exploded. Suburban sprawl created car-dependent communities. Interstate highway systems replaced railways as the primary freight infrastructure. Petrochemicals became the foundation of plastics, fertilizers, and countless consumer products. By 1970, oil had overtaken coal as the world's primary energy source, but even then, coal still generated most of the world's electricity. Oil dominated transportation and industry, while coal kept the lights on. Count the years. From 1859, when Drake drilled that first oil well, to 1970, when oil finally overtook coal, that's 111 years. More than a century for oil to become the dominant energy source, even with revolutionary technologies like the automobile driving demand. And during most of that period, people were still building coal infrastructure, opening new coal mines, constructing coal-fired power plants. The transitions overlapped. Oil didn't wait for coal to disappear. It grew alongside coal, slowly capturing market share, gradually building the infrastructure that made oil convenient and coal obsolete in certain applications. Now let's talk about natural gas, because its timeline reveals something even more important about energy transitions. Natural gas was first made commercially available around 1900, right when coal was at its peak and oil was just beginning its long march toward dominance. Gas had obvious advantages. It burned cleaner than coal. It could be piped directly into homes and factories, eliminating the need to stockpile fuel. It was abundant in many regions where oil drilling also produced natural gas as a byproduct. But natural gas faced a massive infrastructure challenge. You can't transport gas in barrels like oil or rail cars like coal. Gas requires pipelines, extensive networks of high-pressure pipes connecting gas fields to consumers. Those pipelines require huge capital investments, rights of way across private property, regulatory approvals, and decades of construction. And here's the catch. Nobody wants to invest billions in pipelines unless there's demand at the other end. But consumers won't switch to natural gas until the pipelines reach them. It's a circular problem that takes time and coordination to solve. The timeline reflects this challenge. Natural gas became commercially available in 1900, but it didn't reach 20% of the total energy market until 1970. 70 years to capture 1/5 of the market. Compare that to the expectations people had in the 1970s. Energy analysts in that era predicted natural gas would quickly become the dominant fuel, surpassing both coal and oil by the end of the 20th century. They saw gas as cleaner, more versatile, and more efficient. But their predictions were wrong, not because gas lacked advantages, but because infrastructure takes generations to build. The major expansion of natural gas came after World War II, particularly in the 1950s and 60s, when the United States constructed thousands of miles of interstate gas pipelines. These pipelines connected the gas-rich Southwest to the energy-hungry Northeast. Cities that had burned coal for decades converted their systems to natural gas. New suburbs were built with gas furnaces and gas water heaters from the start. But even with massive government support and clear economic benefits, the conversion took decades. By 2008, natural gas still represented only about half of what analysts in the 70s thought it would be by that date. Infrastructure doesn't care about predictions, it moves at its own pace. So let's step back and see the pattern. Coal took 100 years to go from 1.7% of the energy mix to 47.2%. Oil took 80 to 110 years to become dominant, depending on how you measure dominance. Natural gas took 70 years just to reach 20% of the market and is still growing today. These aren't fast transitions. These are generational transformations that require building entirely new infrastructure, training entirely new workforces, and convincing entire populations to change how they heat their homes, power their factories, and fuel their vehicles. And here's the critical insight. Each transition happened faster than the one before it. Coal took a century. Oil took nearly as long, but with steeper growth curves once infrastructure was in place. Natural gas grew faster still in the regions where pipelines were built. The pace is accelerating, but it's still measured in decades, not years. So what does this tell us about solar? Solar energy as a serious commercial technology began emerging in the early 2000s. Yes, solar panels existed before then, but utility-scale solar and affordable residential solar really took off in the 2000s when costs started falling, and government incentives made installation economically viable. Let's use 2000 as a rough starting point, the moment when solar began its climb from nearly 0% of global electricity generation towards something meaningful. In 2000, solar generated essentially nothing in the global energy mix, a rounding error. By 2010, solar had reached about 0.3% of global electricity generation. By 2020, it had climbed to about 3%. And by 2024, the most recent data shows solar at around 7% of total global electricity generation. Look at that growth rate. In 24 years, from 2000 to 2024, solar went from 0 to 7% of global electricity. That's a doubling approximately every 2 to 3 years during the 2010s and 2020s. Now compare that to historical transitions. Coal took 80 years to go from 2% to 47%. Oil took 50 years just to reach 10% from commercial viability. Solar is growing faster than any energy source in history. The question is whether that growth rate can continue and what obstacles might slow it down. Let's start with what's driving solar's rapid expansion. Cost is the biggest factor. In 2010, solar photovoltaic panels cost about $3.50 per watt of capacity. By 2024, that cost has fallen to around 20 to 30 cents per watt, a decline of more than 90%. Wind turbine costs have fallen about 70% in the same period. Battery storage costs, critical for making solar viable at large scale, have fallen 90% since 2010. These cost reductions are unprecedented in energy history. Coal never got 90% cheaper in a decade. Oil never experienced that kind of price collapse. Solar has. When solar becomes the cheapest source of new electricity generation, utilities choose it. When homeowners can install rooftop panels and cut their electricity bills, they choose it. When developing countries can build solar farms faster and cheaper than coal plants, they choose it. Cost drives deployment, and deployment drives further cost reductions through economies of scale and technological improvements. It's a reinforcing cycle that's accelerating solar's growth beyond what historical energy transitions would suggest is possible. But here's where the pattern from coal, oil, and gas becomes relevant. Cost isn't everything. Infrastructure matters just as much, maybe more. Coal became cheap once railways made it accessible, but building those railways took decades. Oil became transformative once refineries and pipelines and gas stations existed, but creating that infrastructure took generations. Natural gas had clear advantages but couldn't scale until pipeline networks were built, a process that's still ongoing in many parts of the world. Solar faces its own infrastructure challenge, and it's massive. Solar panels are getting cheaper and more efficient, but solar energy is variable. The sun doesn't shine at night. It shines less on cloudy days. It varies by season and latitude. This means solar requires either energy storage, batteries that can store excess generation during the day for use at night, or grid infrastructure that can move solar energy from sunny regions to areas that need power when and where the sun isn't shining. Let's talk about the grid challenge first. The existing electrical grid was designed for large centralized power plants, coal plants, nuclear plants, natural gas plants that generate electricity continuously and deliver it to consumers through a one-way distribution network. Flip a switch, and electricity flows from the power plant to your home. Simple, reliable, predictable. Solar changes everything about this model. Solar farms generate electricity during the day, sometimes producing far more than local demand, and produce nothing at night. Rooftop solar on millions of homes turns consumers into producers, sending excess electricity back into the grid during sunny hours. This creates a two-way power flow that the grid wasn't designed to handle. Voltage fluctuations, frequency instabilities, congestion on distribution lines. These problems multiply as solar penetration increases. Solving these problems requires upgrading the grid. New transmission lines to move solar power from sunny deserts to cloudy cities. New transformers to handle variable power flows. Smart grid technology to balance supply and demand in real time. According to the International Energy Agency, achieving global climate goals requires adding or replacing 80 million kilometers of power lines by 2040. That's equivalent to rebuilding the entire existing global grid. The cost estimates vary, but most analyses suggest spending between $1 and $2 trillion per year on grid infrastructure through 2050, far more than current investment levels of about $300 billion annually. Here's where the timeline becomes sobering. New transmission lines take 5 to 15 years to plan, permit, and build. That's 5 to 15 years for each major project. Compare that to building a solar farm, which takes 1 to 5 years, or installing residential solar, which takes weeks. The generation technology is ready. The grid infrastructure to support it at scale is not. And unlike solar panels, which are manufactured in factories and can scale up production quickly, transmission lines require rights of way across private and public land, environmental reviews, local opposition, and coordination among multiple regulatory jurisdictions. It's slow, expensive, and politically difficult. This is exactly the pattern we saw with natural gas. The fuel was available, the technology was proven, but the pipelines took decades to build, and they're still being built today, more than a century after natural gas became commercially available. Solar faces an even bigger infrastructure challenge because it's not just about pipelines or wires. It's about rebuilding the entire electricity system to accommodate a fundamentally different kind of power generation. Now let's talk about storage, because this is the other critical piece of infrastructure that solar needs to reach high penetration levels. Batteries are getting cheaper and better, but they're still expensive relative to the scale of the challenge. A typical utility-scale battery storage facility costs about $300 to $500 per kilowatt-hour of capacity. That means storing enough electricity to power a city for one night costs hundreds of millions of dollars, and that's just for one night. If you want to handle multiple cloudy days or seasonal variations, you need weeks or months of storage, which becomes prohibitively expensive with current battery technology. Some energy systems analysts argue that a fully renewable grid based on solar and wind can work with modest amounts of storage, maybe 10 to 20% of total generation capacity, combined with demand response programs that shift electricity use to times when renewable generation is high and long-distance transmission that moves power from sunny or windy regions to places that need it. Other analysts say that getting beyond about 60 to 70% renewable penetration requires either massive overbuilding of generation capacity, building 2 or 3 times more solar and wind than you actually need so there's always excess, or developing new storage technologies beyond lithium-ion batteries like pumped hydro storage, compressed air storage, or green hydrogen production. All of these solutions take time. Pumped hydro requires specific geography, mountains with water reservoirs. Compressed air requires underground caverns. Green hydrogen requires electrolyzers, pipelines, and fuel cells, essentially building a parallel hydrogen economy alongside the electrical grid. These aren't things that happen in 5 or 10 years. They're multi-decade infrastructure projects with their own permitting challenges, financing hurdles, and technological uncertainties. So when we look at solar's timeline through the lens of historical energy transitions, what do we see? We see a technology growing faster than coal, oil, or natural gas ever did. We see costs falling at unprecedented rates. We see political support in many countries. We see clear environmental benefits. All of this suggests solar will continue expanding rapidly in the near term, probably reaching 15 to 20% of global electricity generation by 2030, maybe 25 to 30% by 2040. But we also see infrastructure constraints that historically have taken 50 to 100 years to fully resolve. The grid needs massive upgrades. Storage needs to scale by orders of magnitude. Supply chains for solar panels, batteries, and grid equipment need to expand. Skilled labor needs to be trained. Regulatory frameworks need to adapt. These aren't problems that technology alone can solve. They require coordination among utilities, governments, manufacturers, construction companies, and communities. And coordination at that scale always takes longer than optimists expect. Historical data from energy transitions shows a consistent pattern. A new energy source starts slowly, grows exponentially during the build-out phase when infrastructure is being constructed, and then growth slows as the source approaches saturation and runs into physical or economic constraints. Coal followed this pattern, oil followed this pattern, natural gas is following this pattern right now, with growth slowing in mature markets even as it expands in developing countries. Solar appears to be in the early part of the exponential phase. Growth rates of 25 to 30% per year are happening right now. But those growth rates won't continue forever. At some point, probably when solar reaches 40 to 60% of electricity generation in a given region, the infrastructure constraints start binding hard. The grid can't handle more variable generation without expensive upgrades. Storage costs become prohibitive. Land use conflicts intensify. Growth continues, but at a slower pace. If we apply the historical timeline from coal and oil, we might expect solar to become the dominant source of electricity, meaning more than 50% of total generation, somewhere between 2050 and 2070. That's roughly 50 to 70 years from when solar began its serious commercial expansion in the early 2000s. Faster than coal's 100-year timeline, faster than oil's century-long rise, but still measured in decades, not years. Some regions might move faster. China is installing solar and wind at extraordinary rates, driven by government mandates and massive manufacturing capacity. By 2030, China might have 50% or more of its electricity from renewables. Europe, with strong climate policies and high electricity prices that make solar economically attractive, could reach similar levels by 2040. But the global average, which includes developing countries with less capital and slower infrastructure build-out, will lag behind these leaders. The United States presents an interesting case. It has abundant solar resources, particularly in the southwest, and rapidly falling solar costs. But it also has a fragmented electrical grid, divided into regional operators with limited coordination and a slow permitting process. For new transmission lines, data from the early 2020s shows the United States installing record amounts of solar and wind, with renewables accounting for more than 80% of new electricity generation capacity added in 2024. But actually connecting all that generation to the grid is taking longer. There are more than 3,000 gigawatts of renewable energy projects waiting in grid connection queues, about 5 times the amount of solar and wind capacity added globally in 2022. Some of those projects will get built, others will be cancelled because the wait is too long or the grid upgrades are too expensive. This disconnect between generation capacity and grid capacity is exactly what happened with natural gas in the mid-20th century. Gas was abundant and cheap, but pipeline capacity limited how quickly it could expand. Utilities and policymakers eventually solved that problem by building pipelines, but it took decades of steady investment. Solar faces a similar challenge with transmission and storage. The technology is ready, but the infrastructure lags. Let's talk about what could accelerate the timeline. Technological breakthroughs in storage could change everything. If someone invents a battery chemistry that costs 1/10 of current lithium-ion batteries and last 10 times longer, solar's infrastructure challenge becomes far easier to solve. If advanced geothermal or next-generation nuclear power can provide reliable baseload electricity alongside solar and wind, reducing the need for storage, that changes the equation. If carbon pricing or regulations make fossil fuels uneconomical, forcing utilities to choose renewables even when infrastructure isn't fully ready, that accelerates deployment. Policy choices matter enormously. Countries that streamline permitting for transmission lines, standardize interconnection processes for renewable projects, and create long-term contracts that reduce financial risk for developers will deploy solar faster than countries with fragmented regulations and political opposition to new infrastructure. Germany's Energiewende, its energy transition program, demonstrates both the potential and the challenges. Germany has achieved high renewable penetration through massive subsidies and strong political will, but it's also faced grid instability issues and relies on natural gas imports to balance variable renewable generation. What could slow the timeline? Political backlash is the most obvious risk. If electricity prices rise because of the cost of grid upgrades and storage, voters might demand a slowdown. If grid reliability suffers during the transition, support for renewables could weaken. If manufacturing capacity can't keep up with demand, driving up the cost of solar panels and batteries, growth could stall. If raw material constraints for batteries become severe, particularly for lithium, cobalt, or rare earth elements, scaling storage becomes harder. There's also the question of what happens when solar reaches high penetration in the easiest markets. Installing solar in sunny regions with high electricity prices is economically attractive today. But as those markets saturate, future growth has to come from less sunny regions, from areas with lower electricity prices where the economics are tighter, or from applications like heavy industry, where electricity from solar and batteries doesn't easily replace high-temperature heat from fossil fuels. Each increment becomes harder, and historical energy transitions show that growth slows as the low-hanging fruit gets picked. China's experience offers valuable lessons. China built the world's largest solar manufacturing industry and deployed solar at a scale no other country has matched. Between 2020 and 2024, China installed more solar capacity than the rest of the world combined. But even China is now dealing with grid constraints. Curtailment, when solar farms have to shut down because the grid can't absorb their electricity, is rising in some provinces. Transmission lines to move solar power from the sunny west to the industrial east are being built, but they take years to complete. Storage deployment is accelerating, but it's still small relative to the amount needed. China's aggressive deployment is pushing the infrastructure limits, and now the focus has to shift to building out the supporting systems. India tells a similar story. Solar costs in India are among the lowest in the world, and the government has set ambitious renewable energy targets. But grid infrastructure in many regions is weak, and financing for transmission upgrades is limited. Projects get approved, but grid connections are delayed. The generation is ready to grow faster than the infrastructure can support. Europe has the opposite problem in some ways. European countries have extensive grid infrastructure and interconnections between nations. But the scale of renewable energy growth is testing even those robust systems. Germany generates so much solar and wind on sunny, windy days that electricity prices sometimes go negative, meaning generators pay consumers to take power because there's nowhere to store it and no way to quickly shut down all generation. The solution is more storage, more flexible demand, and better interconnections to other countries, all of which take time and investment. The pattern across all these regions is the same. Solar technology is ready, solar economics are attractive, but the supporting infrastructure, grids, storage, skilled labour, regulatory frameworks, is struggling to keep pace. And that infrastructure gap is what determines the timeline, just like it did for coal, oil, and natural gas. So what does this mean for someone trying to understand when solar will truly dominate the global energy system? It means you should ignore the optimists who say 10 years and the pessimists who say never, because both are missing the historical pattern. Energy transitions take 50 to 100 years in most cases, measured from when a new source begins serious commercial deployment to when it becomes the dominant source. Solar started its serious growth around 2000, which suggests dominance, meaning more than 50% of global energy, somewhere between 2050 and 2100. But here's the nuance. Solar is growing faster than historical energy sources, so the timeline might be shorter, maybe 40 to 60 years instead of 80 to 100. And solar is growing fastest in electricity generation, which is easier to decarbonize than transportation or industrial heat. So when people talk about solar dominance, they usually mean electricity, not total energy. For total energy, including transportation fuels and industrial heat, the timeline is longer because electrifying everything requires even more infrastructure: electric vehicle charging stations, heat pumps replacing gas furnaces, electric arc furnaces replacing coal-fired steel production. The transition isn't binary. It's not like a light switch that flips from fossil fuels to solar. It's a gradual shift where solar grows from 7% today to 15% in 5 years to 30% in 15 years to 50% in 30 or 40 years, while fossil fuels gradually decline. During that entire period, we'll have a mixed energy system where solar coexists with natural gas, nuclear, hydropower, and some remaining coal. The infrastructure will evolve gradually. The grid will get stronger and smarter over decades. Storage will scale up as battery technology improves and becomes cheaper. Regulatory frameworks will adapt, sometimes quickly, sometimes slowly, depending on political priorities. And here's what coal, oil, and natural gas teach us about that long transition. Every energy source that became dominant created new industries, new jobs, and new wealth in the process. Coal built railways and steel mills and chemical industries. Oil created automobiles and petrochemicals and aviation. Natural gas enabled clean heating and efficient electricity generation. Solar will create its own industries: battery manufacturing, smart grid technology, electric vehicle infrastructure, green hydrogen production. Those industries will drive economic growth, just like coal and oil industries did in their eras. And that economic growth will fund the infrastructure investments needed to complete the transition. The other lesson from history is that transitions aren't smooth. There are periods of rapid growth and periods of stagnation. There are regional differences where some places race ahead while others lag behind. There are technological surprises, both positive and negative. There are political shifts that accelerate or delay progress. Coal growth stalled during economic depressions. Oil growth accelerated during wartime. Natural gas growth varied wildly between regions, depending on pipeline construction. Solar will follow a similarly uneven path, with surges in some years or decades and slower growth in others. What's different this time is the urgency. Coal, oil, and natural gas transitioned over a century because there was no particular reason to hurry. Wood was running out, but not overnight. Whale oil was expensive, but not catastrophic. The transitions happened at the pace that economics and infrastructure allowed. Solar is different because climate change creates a deadline. Scientists say global emissions need to reach net zero by around mid-century to limit warming to manageable levels. That's only 25 years away, not 50 or 100. So the question becomes whether solar and other renewables can scale fast enough to meet that deadline, or whether the historical pace of energy transitions means we'll miss the target. The data from the 2020s suggest we're on track to significantly reduce fossil fuel use, but probably not fast enough to hit the most ambitious climate targets. Coal use is peaking in developed countries and likely peaking globally within the next few years. Oil demand might peak in the late 2020s or early 2030s as electric vehicles scale up. Natural gas will probably continue growing for another decade or two before peaking. Renewables are expanding rapidly, but they're adding to energy supply, not entirely replacing fossil fuels yet, because global energy demand keeps growing. The International Energy Agency projects that fossil fuels will still provide the majority of global energy in 2040 under current policies, though renewables will be closing the gap. To achieve net zero by 2050 requires fossil fuels to decline much faster, which means accelerating the infrastructure build-out for renewables beyond what historical transitions would suggest is realistic. It's possible, technically and economically, but it requires political will, massive investment, and coordination at a global scale. This brings us back to the core question. What do coal, oil, and natural gas teach us about solar's timeline? They teach us that energy transitions are slow, infrastructure-constrained, and uneven. They teach us that cost reductions alone don't guarantee rapid deployment without supporting infrastructure. They teach us that the physical build-out of grids, storage, and supply chains takes decades even when the technology is ready. But they also teach us that transitions do happen. that new energy sources do replace old ones, and that the economic and technological forces driving change are powerful enough to overcome resistance and inertia. Solar is following the same pattern, with some acceleration due to faster cost declines and stronger policy support. But the basic physics of infrastructure haven't changed. You still need steel and concrete and copper to build transmission lines. You still need trained workers to install solar panels and maintain battery systems. You still need regulatory approvals and financing and community acceptance. These things take time, just like they did for coal, oil, and natural gas. If you're an investor or a business owner or a policymaker trying to navigate the energy transition, the historical pattern gives you a framework. Expect solar to keep growing rapidly in the near term, reaching 15 to 25% of global electricity by 2035 or 2040. Expect infrastructure constraints to become increasingly visible as solar penetration rises, creating bottlenecks that slow growth unless addressed. Expect regional variation, with some countries moving much faster than others based on resources, policies, and grid capacity. Expect the transition to extend over several more decades, not finish in the next 10 or 15 years. And if you're just someone trying to understand where the world is headed, the lesson is clear. The energy transition is real. Solar is winning on economics and will continue expanding. But the timeline is longer than optimists claim because infrastructure always takes longer than technology. We're in the middle of the fourth great energy transition, following the paths that coal, oil, and natural gas blazed before. The destination is increasingly clear, a world powered primarily by renewable electricity. The journey is long, complex, and uneven, just like every energy transition that came before. The pattern doesn't lie. 50 to 100 years for historical transitions, maybe 40 to 70 years for solar if everything goes well, maybe longer if infrastructure challenges prove harder to solve than expected. That's the lesson from history, not a guarantee, not a prediction, but a pattern based on the physical realities of building energy systems at civilization scale. Coal taught us that transitions take a century when starting from scratch. Oil taught us that even revolutionary technologies like automobiles don't speed things up as much as people expect. Natural gas taught us that infrastructure bottlenecks can delay growth for decades, even when the fuel is abundant and cheap. Solar is teaching us that cost reductions can accelerate the early stages of a transition, but eventually you run into the same constraints that slowed down every previous energy revolution. The grid, the storage, the supply chains, the skilled labor, the permitting processes. These aren't problems you solve with better solar panels. These are problems you solve with sustained investment, political commitment, and decades of patient work building the infrastructure that makes a new energy source truly transformative. So when someone asks you when solar will take over, tell them the pattern. 7% today, 15 to 20% by 2030, 30 to 40% by 2040, possibly dominant by 2050 to 2070. Faster than coal, faster than oil, but still measured in decades, not years, because that's what every energy transition in history teaches us. The fourth great energy transition is happening. Just don't expect it to finish before your grandchildren are grown, because energy systems don't change overnight. They change over generations, one power plant, one transmission line, one storage facility at a time, until one day you look around and realize the world runs on sunlight, just like it once ran on wood, then coal, then oil, each transition taking its time, each transition reshaping civilization, each transition following the same patient, relentless pattern of growth that infrastructure allows and physics demands. If this documentary gave you a different way to think about solar's timeline, if you can now see the pattern that connects coal's century-long rise to solar's current trajectory, if you understand why the question isn't whether but when and how long, then you're starting to see energy transitions the way history actually works. Subscribe to see more patterns that reveal how the cycles that shaped our past are already telling us about our future. Because the energy transition isn't just happening in solar panels and wind turbines, it's happening in grids and batteries and supply chains, in regulatory offices and construction sites, in the same slow, determined way that every great transformation in energy has always happened. The pattern is clear, the timeline is long, and the transition, whether we're ready or not, keeps moving forward.